Right. Hello, everybody, and thank you very much for inviting us here. This is an awesome workshop. I'm learning in every talk. I'm going to talk about dopaminergic secret for perceptual decision. As Javier said, we are going to change to a little bit of neural gear here. Dopaminergic, dopaminergic neurons are neurons which are majority of them are sitting in substantia nigra and ventral tegmental area. A relatively small number of neurons, but they have profound effect on the behavior. You could think of old work from Old and Milner, in which they showed that animal would do anything to get this type of dopamine stimulation. They have different effect and different role in behavior. We know that they are regulating actions, they are regulating motivation, and they have important role in the process of learning. In the context of learning, the activity of this neuron at the time of conditioned stimuli and unconditioned stimuli is very much conceptualized to encode the reward prediction error. And that is, as you guys know, the difference between what animal was predicting and the reward that animal eventually received. So this term, this simple term is central in theories of reinforcement learning. It's really guiding the agent to make better prediction and therefore better choices in the future. So one thing which is important when thinking about this conclusion is that the majority, okay, too many. All right. The majority of the work and the majority of experiments which are leading to this conclusion are coming from behavioral tasks which we call economic decision making or value-based decision making. So that is the situation that the animal is challenged to make the choices between action or a stimuli which gives the best reward. So in this type of behavior, you're really manipulating the properties of reward, the magnitude of the reward, the probability, the delay, and so on and so forth. And stimuli or action are often visible and easy to do for the animal. And that's fine, but of course, it's not the only type of decision that we make. We also, okay, it's going a little bit too fast. Okay, so what is important here to know is that, going back to this equation, so the idea here is effectively those predictions are those which are learned. Animal is sampling previous actions, animal is sampling previous stimuli, and it's effectively making predictions based on those learned values. And it would compare those learned values with the eventual outcome. As I said, these are not the only type of decision that we make. We also make perceptual decisions. These are the type of decisions in which we rely on current sensory evidence in order to make choice. So when we have animals in this type of task, the animal is really challenged to detect or discriminate the currently available sensory evidence and make a choice based on that. And in this type of behavior, we often have the reward structure to be simple, like none or one. So relative to economic decision, we know much less about the activity of dopamine neuron in this type of task. Going back to this equation again, one can really think that the predicted reward here is something that the system needs to estimate online. So it's very different from the learned. And we need to evaluate the ambiguous sensory stimulus, and it would need to generate a prediction about the upcoming reward based on those information which are immediately available. So the question is, can dopamine neuron access those type of information? Can they compute prediction error which incorporates this perceptual ambiguity into the calculation? So I will be getting into this by first asking what are the dopamine signals at the level of midbrain during perceptual decisions. We're getting a little bit later into the circuit by asking the question of whether different projections of dopamine neuron to different regions of the striatum encode different information during perceptual decisions. And at the end of my talk, I will be talking very briefly about the work which is currently happening in the lab, as well as things that we can do together. So to get to the question of the dopaminergic activity during perceptual decision, we use this behavioral task that we previously designed together with my colleagues back in London. So this is a head fixed task for mice, and there is a screen in front of this mice. There are stimuli coming either on the left side or on the right side of the screen. And the task for the animal is to report where this stimulus is. And it will get a reward for correct choices. And just to make the task harder or easier in different trials, we are changing the contrast of the stimulus in different trials. And that's an example psychometric function. You can see that these animals, after some training, they can perform this type of task quite well. Okay, so having this behavioral task, having this perceptual task, or in general, any perceptual task, kind of 2AFC perceptual task. The question is, how can we define reward prediction error in this scenario, which relies on those incoming sensory signals? So to get to this, we developed a simple reinforcement learning model. You can think of it as a Q-learning model, but with one extra feature. And that feature is that the model is getting an element of sensory confidence or a statistical sensory confidence on every trial. So what is happening is that the stimulus is coming in, and you're using Bayesian formalism in order to calculate trial by trial internal estimate of whether the stimulus is on the right side or on the left side. And those probabilities are coming to be multiplied by the learned value of left and right action. This would define action values, lead to a choice, prediction. This prediction is compared with the outcome to create prediction error and the updating to happen. So this model has two important internal variables here. One of them is predicted reward, and the other one is prediction error. And we can see that in case of predicted reward, so here we have the stimulus from hard to easy. We can look at the correct rewarded trial as a function of contrast of the stimulus, or as the stimulus is getting easier, those predictions are increasing and they are different and lower in the error trial. And in case of prediction error, reward prediction error, you have a rather mirror image. So that is the situation that the model is receiving the reward, but the size of the prediction error is adjusted based on how confident that agent, that model was in getting the reward. So this model has rather non-intuitive prediction about trial-by-trial learning, as you can guess. So having this prediction error here, this is, as I said, this is a situation that the model received the reward. Once it was after the easy trial, so the size of the positive prediction error is rather small. This is leading to small updating of the values, and this would be a small or no change in the psychometric curve. So the psychometric curve conditional on this situation would be rather similar to the average psychometric curve. But if we look at the behavior of this model, after hard trial, the model got the large prediction error. This is leading to large updating of one of the action values, and therefore a larger shift of psychometric function condition after successfully performing this hard trial. So that's model prediction, and we saw very similar effect in the data from our mice. So these guys are changing or shifting the psychometric function depending on how difficult was the previous choice. If the previous choice was difficult and they managed to get the reward, that is the situation for them, that they learn something from it. And the signature of learning here is a shift of psychometric function. You might realize that this is actually not a good type of learning to do in this context. These trials are independent from each other. But nevertheless, even in the asymptotic behavior, you still observe signature of this across population. So we then ask the question of what is dopaminergic in VTA doing during this type of task? So we image the bulk activity of neurons in VTA, dopamine neurons in VTA, and what I'm showing here is the activity of those neurons at the time of a stimulus and at the time of outcome, and they are separated the way that I separated the figures from the model. So the circles are dopaminergic activity, and the shaded areas are the estimates from the model after fitting on the behavioral data. So you can see that both at the time of stimuli as well as the time of outcome, this neuronal activity is incorporating the statistical confidence or sensory confidence in calculating both prediction as well as prediction errors. So having shown that the next question that we try to get to is what is happening in a subpopulation of this neuron defined based on the projection pathway. So we know from anatomy that these neurons in ventral tegmental area and substantia nigra, they are forming rather subpopulations which are projecting to different regions. And we know from previous work that they recorded the activity of dopamine axon coming to dorsal striatum or coming to ventral striatum. So this was a simple passive task. Animal was just passively locomoting sometimes it was receiving reward. And what we can see in this data is that the axons which are coming to dorsal striatum, they are driven by the locomotion. Whereas the axons which are coming to the ventral striatum, they are mainly driven by reward. So Peter and Morgan in the lab, they try to record the activity of these neurons during our perceptual tasks, which also include the stimuli and the ambiguity of those stimuli. And to do so, they again image the activity of these neurons, but this time they image the activity of axons, which are going to dorsal or ventral regions. And in case of ventral striatum, what we observed was actually very, very similar to what I showed you before in VTA. So the responses at the time of a stimuli are increasing as a function of contrast of the stimulus. And it doesn't really matter if they are ipsilateral or contralateral. They're really, at the time of a stimuli, really encoding the expected reward that animal is expected to receive. I'm not showing that many plots here, but this is overall very similar to VTA. And it's expected because from VTA to VTA, there is a strong projection to nucleus accumbens ventral striatum. In case of dorsal striatum, however, we observe something which is qualitatively different. So what we observe is that these axons of dorsal striatum, they are only responding at the time of a stimuli which were contralateral to the recording. And they were scaled in that condition with the contrast of the stimulus. So having these contralateral responses, the first thought that we had is like knowing that this dorsal ventral striatum is really important in the preparation of the action for the animal. Our concern was that this is not really about the stimulus. This is about the animal preparing to generate a lateralized action. And we try to get to that by training this animal in another version of the task. So in this version of the task, animal actually learn to not move this wheel. So before the stimulus onset, they were not moving the wheel, and they were not moving the wheel for a second after the stimulus. And we could still observe these contralateral visual responses in dopamine axons, which are innervating dorsal striatum. So I'm showing this to motivate the fact that we really need to think about the subcircuit of this neuromodulator in order to better understand the function. And it's also important to note that this is what we are observing in the visual task, in which it's actually possible to define lateralized stimuli. We know, for example, from work of Uchida's group, that if you use olfactory stimuli, in which the lateralization of the stimulus is harder to judge, or it's not relevant, then we don't see such an effect. Okay, so I'm going to spend a few more minutes here on thinking about where we should go and where my lab is currently going and where we should go collectively, at least where I think we should go collectively. So one of the issues is the fact that we have been really ignoring the process of learning from naive state to expert behavior. So the majority of neural data that we have is really coming from situation that we get the animal to the lab, we train the animal to the expert behavior. And then we are testing learning here by changing a small aspect of the task. But for example, we change the meaning of the stimulus for the animal, or we make the reversal in the action. So it is really the type of learning that we have been investigating so far is really a type of fine-tuning of already learned behavior. And that is very, very different from what is happening to an animal which is coming to the lab, which takes ages and days and weeks in order to learn a simple behavior. So that's kind of getting to what Javier was mentioning. In this situation of learning from scratch, animal really needs to think about the task, the strategies for performing the task. And that is a situation that we relatively know much less, both in terms of dopaminergic activity and in general about the neural activity. Thinking about this learning from naive to expert, the other problem is that even the behavioral data that we have so far on our hard drives is really not that useful. And the reason for this is that the way that we have been working with this animal is what we call shaping. So we get the animal into the lab. On the very first day, the task is very simple. The second day, the task is getting harder and harder and harder. And that's what we call shaping. And it's an excellent method for getting this animal to expert behavior very quickly. However, it does not allow us to directly compare neural activity. And it's, of course, is masking the possible strategies that that animal might have in order to learn and perform the task. We're really pushing the animal to the particular expert behavior with a sharp psychometric function, and that's what we get from shaping. So, with these two limitations in mind, a group of brave people in the lab started recording from the release of dopamine in different regions of the striatum in animals from the first day till the expert behavior in a complete perceptual task. And that is the collaboration with our collaborators, both experimental and theoretical collaborators. So thinking about the task, it's a hard situation because you can have either very easy task and animals are learning it from day one, or you can have a very complicated task and they never learn it. But the idea is that to never change the task throughout this learning. So with some preliminary work, we got to a situation that we can have a task which has full psychometric function. We introduce animals to this task from day one without changing any timing or introducing any stimulus or changing reward or anything. And animals learn to managed to learn this task after days. So this is the data from many animals here. What we are having here is like each of those lines are one animal, and then for simplicity we're plotting this as 4 quadrants of learning. So there might be the case that one animal takes 30 days, one animal takes 10 days, but we're plotting it just for simplicity here. And what we can observe is that the psychometric function are slowly getting steeper and steeper, and reaction times are going faster and faster in that situation. Throughout this behavior, we have been, as I mentioned, we have been recording the activity of dopamine, and in this case, the release of dopamine. Let's see if it's working. It should work. Okay, kind of, yes. Okay. So we have been taking advantage of genetically encoded dopamine sensors in order to record that the release of this neurotransmitter across different regions of the striatum. What I'm showing here in this video, which was supposed to be very smooth, but apparently it's not, is an example recording in which we are recording simultaneously from the left side and the right side dorsolateral striatum, measuring the release of dopamine in the task. And what we are trying to do right now is we're working with our collaborators in order to, and students in the lab, in order to create models, computational models, which can underlie the process and the dynamic of the behavior, and use these computational models in order to understand the neural activity that we are observing. The other issue that I would like to briefly touch on is the question of how to do collaborative work. And we are all concerned about the idea of replicating data and the difficulty about that. And one approach to tackle this problem is to effectively standardize tasks across labs. And this is a situation that many labs would run one behavior and one neural recording experiment in order to test the replicability. Of course, it's very valuable both inside neuroscience and outside neuroscience. It would ensure that things can be replicated. It has the power of large data, and that allows hypothesis testing, which is otherwise not easily possible. But it also comes with a major limitation, and that major limitation is that the results are too specific. If I record whole brain during this behavioral task that I have, or any other behavioral task, the result will be very specific to that modality, that sensory modality, and that effector that we have for execution of choice. So the result would be, as I said, specific, and of course, this is costly. But I'm going to suggest something which is obvious, and that is the fact that we have already a lot of data. In particular, in perceptual decision making, we have been doing this for 20-30 years. I think we have enough data in a standard type of behavioral task across the species to do things together. This would ensure replicability. Of course, the data would be large. The result, we would be scared that the result will be noisy, but if we get results, then they are general. They are not going to be suffering from the fact that they are effector specific or modality specific. And as obvious it sounds, but I would like to be a little bit specific here, and in particular in systems neuroscience, we are often worried that when we are doing that, looking at neural activity, we are often worried that, okay, is this a stimulus responses or is it the action which is following the stimulus? So we are struggling with this type of data analysis all the time. And the solution to this is effectively use different data sets with different effectors, with different sensory modalities, and see to what extent the finding is holding. And I'm going to show you an example in which I have for the utility of this approach. So what I showed you here, what I showed you before, was this behavioral effect, this learning effect, in which the amount of trial learning was regulated by the confidence of the animal in the previous trial. So with collaborators, we tested this idea across different sensory modalities, across different species. We don't really need to learn that figure, but these individual dots are individual subjects, and anything which is above 0 is effectively quite similar effect that we are observing here. So what we can see here is that rather subtle effect, which is a rather small shift of psychometric function, it can still hold across different modalities, across different species, and across different tasks, head fixed or freely moving. And I was very happy to see that others who later did the same analysis on the data, they actually found quite similar effects. So the figures are like not matching, they're from different, but it is all the same effect. So I would like to invite everybody to think about this, and if there are enough momentum on this, we can do things in a rather easy way. We really need 20 or 30 data sets from different species all in one place, starting with the behavioral data in order to actually test a hypothesis that we probably cannot test otherwise. To finish, I would like to summarize what I showed you. So I talked about this confidence-dependent choice updating. It's a new form of learning that we have described. It depends on the past difficulty of the choice, and you could see that it's observing across the species and tasks. I briefly showed that this choice updating is explained by RL models, which incorporate an element of a statistical decision confidence. And we briefly touch on VTA dopamine activity and the projection to ventral striatum that seems to encode this type of prediction errors. With that, I would like to thank you for listening. Thank you, my lab. It has been fantastic. We went through pandemic together, and we are out of it. Past members, collaborators, my funders, and a small announcement. We just had ERC grant, and we have opening in the lab for both postdocs and RA if you're interested in this type of work. Thank you very much.